What's up guys, it's Iman Fiaz and today's video is on AQA AS level chemistry June 2017 paper 1 walkthrough section 8 only. Write the full electron configuration for each of the following species. Now we have a table for this. And if I look at the periodic table, I can see that chlorine has 17 electrons, but because Cl minus is going to have 18, so 1s2, a 2s2, 2p6, 3s2, 4, 10, 12, 3p6. Perfect. Now Fe2 plus, well, Fe has got 26 electrons, going to have 24. This is 18 negatively charged electrons, going to have 24 Fe2 plus. 1s2. So I can basically copy and paste, obviously, this first part. Then I need 24, so in 4s2, 3d4. Right? No. But then what happens is that this one 4s2, that becomes 4s1, and this becomes 3d5. Wait, 1s2, 2s2, 2p6, 3s2, 3p6. Actually, this is going to become 3d6 instead. 3d6 instead. I was using the special rule for chromium. And this is iron, not chromium. Right, equation state symbols, third ionization energy of manganese. Say which element is magnesium. Aluminium has the lower first ionization energy. Magnesium, aluminium. Magnesium 1s2, 2s2, 2p6, 3s2. But then aluminium 1s2, 2s2, 2p6, 3s2, 3p1. So it's actually going to be aluminium because its outer electrons in 3p orbital. Aluminium outer electron is in a 3p orbital. And what does that mean? Further away from the nucleus, so easier to remove the outer electrons. Symbols increase mass number of iron that reach detector first. Well, I know it's nickel, so it's going to be Ni. Mass number first is going to be 58 Ni. And because it was electron impact, 58 Ni plus. Calculate some atomic mass of this. I've just double checked they all add up to 161 plus 29.1 plus 9.9. It does, then all I'm going to do is 58 times by 61.0 plus 60 times by 29.1 plus 61 times by 9.9 divided by 100. One decimal place, 58.9%. And the answer must be to one decimal place only. Find equation state symbols for reaction enthalpy exchange equal to enthalpy formation of iron oxide. So Fe2O3 solid, I'm forming that. So 2Fe solid plus 3 over 2O2 gaseous. 2Fe solid plus 3 over 2O2 gaseous, Fe2O3 solid. Calculate standard enthalpy formation, so enthalpy products minus reactants. Delta H is minus 19. And that equals the products. Well, Fe is 0. Look at that. Enthalpy products, 3CO2. Well, CO2, so I've got minus. CO is minus 1 by 1. CO2, so it's going to be minus 222 times by 3. So 3 minus 222. Enthalpy products minus. Oh, no. I don't have that. I'm trying to find it out for carbon dioxide. I can't use carbon monoxide for carbon dioxide. I thought it was just, that's one CO, so CO2. No, that's wrong. So minus 19 equals 3y. That's what I'm trying to find. Minus entropy of products. Minus entropy of reactants. Products minus reactants. Minus 822 plus minus 333. Because minus 111 times by 3 gives 3 moles. I get minus 822 plus minus 333 minus 1155, but because minus that becomes positive, then minus 19 minus 1155 divided by 3 minus 391 kilojoules moles per minus 1. And it's imperative you don't fall for these negatives. Two negatives make a positive mistake. Right, use data table 3 to calculate bond entropy for NH and ammonia. Well, I know delta H is minus 92. I want to find bond entropy for NH and ammonia, so I can say minus 92 equals energy required to break bonds plus, I've got 3H2, so plus 436 times by 3 minus energy released from new bonds are formed, so minus 6 NH bonds. And I get 391, positive 391, because what happens is that's negative 6 NH bonds. Add that to this side, and then I can say 6 NH equals 944 plus 436 plus 92. Give one reason bond entropy calculated in question 2.2 is different from the mean bond entropy code in data book value. Data book value is derived from a number of different compounds. Question 3.1, show by calculation which reactant is in excess. I've got this much of zinc sulfate, so first things first. Moles of zinc sulfate, so it's going to be 50 divided by 1000 times by 0.10, times by 1.00, and 2 moles of magnesium. Magnesium mass of the MR, which is 24.3. So which reactant is in excess? It's a 1-to-1 molar ratio, so it's just basically the one that's got more moles, right? That's 0.05 moles, and this is 0.0856. So reactant excess is magnesium. Zn zinc sulfate, ZnSO4. Then use the data to calculate experimental value for entropy of reaction. Well, delta H, which is Q divided by number of moles, and Q equals MC delta T, where M is the mass of water. I want to find out entropy of reaction, yeah. Mass of water, well, I know I've got 50 centimeters cubed of that. So the mass of water, 1 gram per centimeter cubed, is going to be 50 times by 4.18 times by the temperature change, which is that minus that, so 61.2 minus 23.9. So 50 times by 4.18 times by 61.2 minus 23.9. Then I get my answer, Q delta H, right? But Q needs to be in kilojoules, so divide by 1000. And then I get, wait, let me try this again. So 50 times by 4.18 times by 61.2 minus 23.9. 50 times by 4.18 times by 61.2 minus 23.9. Divide that by 1000. Okay, I get Q as 7.7957 divided by the number of moles. Was the number of moles of what? The number of moles of magnesium or zinc sulfate. Number of moles of zinc sulfate, because magnesium is in excess, right? So divided by 0.05. Then I get my answer 156. But the final thing is that needs to be a negative because temperatures increased. Exothermic temp increases. Suggestion was like the difference with the large difference between students' value and experiment and the data book value, heat loss. Such a student method analysis could be improved to make more accurate value for enthalpy reaction. So stage 1, improved insulation. Alhamdulillah, insulate the beaker. Use a polystyrene cup to reduce heat loss. Stage 2, improved temperature reading. Record the temperature for a suitable time before adding the metal to establish an accurate initial temperature. And then record temperature value at regular time intervals to plot temperature against time on a graph. Stage 3, improved analysis of results. Extrapolate cooling always back to the point of addition to establish a theoretical maximum temperature. And there you go. Question 4.1, deduce in terms of X amount of moles of R in equilibrium mixture. Well, I know X moles of P had reacted, so for R, two X. Okay. 4.2, 298 Kelvin value of Kc is that. Calculate value for equilibrium concentration of R. So concentration of R, first thing I would say is that 3.6 equals concentration of R, which is R, the number of moles of R, is 2x divided by the volume over 1. All of the volumes are 1, so the volumes will actually cancel out. So 2x squared divided by P, which is P. Oh, sorry. It says amount of moles of P in each in P and Q at equilibrium is that. So it's going to be 1 minus x squared. Square root both sides, square root 3.6 and 2x over 1 minus x. So then I get square root of 3.6 times by 1 minus x minus square root of 3.6x equals 2x. Then I can say square root of 3.6 equals 2 plus root 3.6. I get that as x, and then I can say x equals root 3.6 divided by my answer at 0. So I get that, then I say 2 plus root 3.6, and I get 3.897x, and then to find out x is going to be root 3.6 divided by my answer, 0.49, and that's x by 1r, which is 2x, so it's going to be 2 times my answer, 0.97. Was P minus cube. Give the meaning of the term electron negativity. The relative tendency of an atom to attract a pair of electrons in a covalent bond. Then how permanent dipole-dipole forces rise between hydrogen chloride molecules. First thing you need to say, difference in electronegativity leads to bond polarity. Dipoles don't cancel out, hence the molecule has an overall permanent dipole. So attraction between delta positive on one molecule and delta negative on another molecule. There was a question similar to this in the previous past paper, maybe the one before that, and it was like introduce the type of intermolecular forces in SiF4 van der Waals and explain how it forms. Uneven distribution of electrons, one molecule induces a dipole and neighboring molecules. Dipoles cancel out. Symmetrical molecules completely symmetrical, and that's what you say. But in this case, permanent dipole forces, I want to compare it. In this case, well, difference in electronegativity leads to bond polarity. That's number one important thing. And then say, therefore, the molecules of dipoles don't cancel out, so molecules are overall permanent dipole. So there's attraction between delta positive on one molecule and delta negative on another molecule. There's a bond polarity. Dipoles don't cancel out. Molecules are overall permanent dipole. Attraction between delta positive one molecule and delta negative another molecule. Name of this shape and tick if it has a permanent dipole. SiH4, no. pH3, yes. These two are completely symmetrical. The names of the shapes, so you need to do all of them. Tetrahedral, pyramidal, linear, tetrahedral. And you know what? I do need to review the shapes of molecules topic, because obviously this is an AS level question, but in A level papers, like, you need to know the bonds and 3D shapes as well. And yeah, so probably need to review that as well. Balance equation for two stages in process. 4 plus 9.5 over 2. 4 SaO2, C2, C2O, 7 SO2, 4 FeSiO3, 2, 6 SO2. So there's two reasons why the sulfur dioxide byproduct of this process is removed from the exhaust gases. And number one thing you would say prevents acid rain. That's respiratory problems. Another thing is reduces waste product. Prevents acid rain, which damages buildings. Reduces waste product, or you could say toxic. But yeah, there's plenty of reasons why. Passenger jet contains this much mass of copper wiring. Rock sample contains this much of copper sulfur FeS2 by mass. Calculate the mass of this plus 1 copper wire. So what I'll do first is moles of copper, 4050 in grams, 123. That's 4.5 million grams. Divided by the MR of that, 63.5. Put on the calculator, 4050, 123, 63.5, and you get 63780. And that's moles. Then I know a rock sample contains this much of CuFeS2 by mass. And I want to find out the mass of rock needed to produce enough copper wire for passenger jet. So then I'd say, okay, so it's a 1-to-1 mole ratio. I want to find out the mass of CuFeS2. What's going to be the moles, which I just worked out, times by the MR. Then I want the mass in tons of rock needed to produce enough copper wire. So I've got the mass in grams. Then I need to realize, okay, it contains this much CuFeS2 by mass, so times by 100 divided by 1.25. There you go. And then the mass in tons, well, then I need to divide it by 1,000 to go into kilograms, then divide it by 1,000 again, and I get 936 tons. The mass of ore, the mass of rock. Percentage, calculate percentage atom economy for production of copper. So percentage atom economy is the MR of desired products over MR of or reactants times by 100, right? And I want production of copper, which is that. But remember, for percentage atom economy, I include the number of moles, and that's really imperative. So I include number of moles. So for example, for the MR, I'm going to include the number of moles. So it's going to be 2 times by 63.5 divided by MR of all reactants. Well, 2 times by 63.5 plus 16 plus 12. So I'll just convert 63.5 plus 63.5 over 63.5 plus 63.5 plus 16 plus 16 plus 12 times by 100, percentage 74.3%. So just memorize the formula, MR of desired products of MR or reactant, and remember to include the number of moles when timesing by MR, and obviously because percentage, let me do times by 100. Question 7, suggest identity of the group 2 metal ion present in solution Y. It says an aqueous solution Y is contained in one type of group 2 metal ion and one type of negative ion. And I know and then aqueous sulfuric acid to separate solutions of solution Y, and I know it has a white precipitate with sulfuric acid. So it's going to be Ba2 plus. And then ionic equation, Ba2 plus aqueous plus SO42 minus aqueous to form Ba for solid. System identity of negative ion present in solution Y, the OH minus ion. Ionic reaction that takes place by magnesium nitrate is added to solution Y. Magnesium nitrate is added to solution Y. So magnesium nitrate, the Mg2 plus ions, and I'm going to form plus the OH minus ions, but two of them because I'm going to form the magnesium hydroxide. Give the oxidation state of nitrogen following species: NO2 minus plus 5 in NO plus 2. Half equation for the conversion of NO2 minus an acidic solution into NO. So it's going to be, I need to add one water molecule here, but I've got 2H pluses, then I add 2H pluses plus E minus, wait, plus 2 plus 1, so plus E minus again, plus E minus. So NON, and nitrogen, nitrogen, oxygen, oxygen, 2 oxygens left side, 2 oxygens right side, 2H pluses, and then balance charges. Right, conversion of I minus into iodine. I need 2 here, that's the first thing, and then realize, okay, and then I need 2 negatively charged electrons on the right side. Right, overall ionic equation. So first thing I need to do is times by this first equation by 2, so we get same number of electrons. So I get 2E minus plus 4H plus 2NO2 minus to form 2NO plus 2H2O. Then I add them all up together, so I can say 2I minus, because the two negatively charged electrons cancel out, 2I minus plus 4H plus 2NO2 minus to form 2NO plus 2H2O plus I2. And now I'm always going to do this. Is everything, does something appear on both sides? In this case, no. Oh, I don't know why I wrote plus 5 there. It's plus 3. Silly mistake. Oxygen minus 2 times by 4 minus 4. And then that's minus 1. So then it must be plus 3. That's the plus. Yeah. And then that's obviously correct. E minus plus 2H plus NO2 minus form NO plus H2O. And then 2I minus I2 plus 2E minus. 2NO2 minus plus 4H plus 2I minus to form I2 plus 2NO plus 2H2O. And remember, once you've written the overall ionic equation, check if anything appears on both sides is the same. Or if it's like 4H pluses on the left hand side and 6H plus on the right hand side, cancel the 4H pluses on the left hand side and then you're left with 2H plus on the right side. Because that I've seen a question like that and I fell for that mistake, and it's annoying because you don't know this, you feel like you got it correct, but it's that final step just to make sure it is. To state the role of NO2 minus in the reaction with I minus. So oxidizing agent. Oxidizing agent. Calculate concentration grams per dm minus cube of sodium nitrate in a sample. So I know that 25 centimeters cube sample of aqueous solution of sodium nitrate got this much of potassium chlorate. So first thing I would do is, what am I even trying to find? Nitrite ions. So nitrite ions react to acidified chlorate ions according to the equation. I want to find the concentration of that. So first thing I would do is 27.40 divided by 1000 times by 0.0200, and I'll get 5.48 times by 10 to the power minus 4 moles. Then I've got a 2 to 5 mole ratio, so then do my answer divided by 2 and times by 5. And I've got 1.37 times by 10 to the power minus 3 moles of the nitrite ions. I want to find out the concentration. So moles is concentration times by volume. Concentration is moles divided by the volume, which is that 25 centimeters cubed. So 25, but in moles per minus cubed times by 10 to the power minus 3. The answer divided by 25 times by 10 to the power minus 3. That will give me the concentration in moles per minus cubed. So that's the concentration in moles per minus cube. If I want concentration in grams per minus cube, in order to go from moles per minus cube to gram per minus cube, I need to divide by the MR. So sodium nitrite, what's the MR of that? Well, sodium nitrite, so it's going to be 0.048 divided by the MR of sodium nitrite. Well, sodium nitrite, let's think about it. So I've got NO2 minus oh right, because sodium nitrite, I've got sodium and nitrite ions. So this is going to be NaNO2 then. NaNO2 then. So then 0.0548 divided by NaNO2, so the MR of that, 23 plus N, 14 plus 16 plus 16. And then I get 7.94. No, sorry. If I want to convert from moles per d minus cube into gram per d minus cube, I don't divide by the MR, I times by the MR. So then I'm timesing by 23 plus 14 plus 16 plus 16, which is 69. So 0.0548 times by 69, and I get 3.78 grams per d minus cube. That was a major mistake. 0.0 moles per d minus cube, let's do it again. Grams per d minus cube times by the MR. And that is the end of section A. I just want to go through again one question I went through already. This one, permanent dipoles have force derived between hydrogen chloride molecules. Difference in electronegativity leads to bond polarity. Dipoles don't cancel out, molecules are overall permanent dipoles. Attraction between delta positive on one molecule and delta negative on another molecule.